This pair of scissors will outlast the hands that made it, but only if every strike lands at the right moment, at the right temperature, with the right force. Before automated assembly lines, before precision stamping machines, the scissor blade began as something far more elemental. A steel rod, an open flame, and a hammer that fell with the full weight of industrial consequence. In the workshops of the German Bergisch land, nestled between forested hills and fast-moving rivers, an entire economy was built around a single material, steel. As far back as the 15th century, this cluster of towns had earned a reputation that spread across Europe, not for its size, but for the precision of what it produced. By the 19th century, these workshops had made the region the world's largest producer of scissors. The rivers supplied mechanical power, the forests supplied fuel, and a concentrated pool of generational craft knowledge supplied something that could not be imported: judgment. But most people never consider the first step. Before a scissor blade could be sharpened or assembled, it had to be born, forced into existence from raw steel by a process so precisely engineered that one miscalibrated die could ruin an entire production run. How did they do it? And why does this method still produce something that modern shortcuts struggle to match? The die sinker did not work at the forge. He worked before it. In a quieter workshop, he machined the steel molds that would give every blank its form. He learned how to read the tolerances of metal the way others read text. A fraction of a millimeter too wide, and every blank that followed would be flawed. His work was invisible in the finished product, but everything depended on it. The process began with steel rod stock, long bars of carbon steel, uniform in diameter, cut into sections of exact, predetermined weight. This first step was unforgiving. Too much material, and the die would overflow. Too little, and the blank would be undersized. Incomplete in the blade or in the bow, the looped handle through which a finger would one day pass. The cut billet was then placed into a furnace and heated above 1,100 degrees Celsius. At this temperature, steel transitions from rigid to workable. It glows deep orange. The window of optimal malleability lasts perhaps 60 seconds. The heated billet was transferred immediately to the drop hammer. The drop hammer was not a crude instrument. It was a calibrated system. The die, fitted to the hammer, drove into the red-hot steel to form the blank. The pressure simultaneously shaped the metal and strengthened it, compressing its grain structure in ways that casting could never replicate. But the margin was narrow. If the billet had cooled beyond its forging temperature, the steel would resist the die. Cracks could form, invisible at first, catastrophic after hardening. If the billet was misaligned, the blade profile would shift. The bow would be off-center, the entire blank useless. Typically, several blows were required, each refining the form as the metal cooled incrementally. The worker had to read the steel by eye and by sound. One strike too few, and the blank was incomplete. One strike too many, and the die itself could be damaged. Then came the moment the blank became itself, the final blow of the drop hammer. The upper die descends. Steel fills the cavity. The excess and the flash is forced outward in a thin, bright ring along the parting line. The blank is lifted from the die, still hot, still glowing at its edges. For the first time, it holds the unmistakable silhouette of a scissor blade. By the early 20th century, steam-powered drop hammers were the dominant technology for forming scissors from steel rods. Entire factories were organized around this single operation. Yet, as output scaled, something quietly shifted. The knowledge required to maintain the dies, to read the temperature, to judge the hammer, that knowledge became harder to transfer. And once it was gone, it rarely returned. The blank, once cooled, was not finished. It was barely begun. The flash, the ragged fringe of excess steel, had to be removed entirely. Workers fitted trimming dies beneath a punching press and drove each forging through, shearing the flash cleanly along the parting line. This required its own matched tooling, prepared in advance by the same die sinkers who had shaped the forging dies. After trimming, each blank was inspected, checked for surface cracks, measured for dimensional accuracy. The bow was examined for symmetry. A hole was drilled or punched at the pivot point, the location where two finished blades would eventually be joined. Only blanks that passed moved forward. The rest were returned to the furnace or discarded. The difference between a competent forge worker and a master showed up later, after hardening, after grinding, after years in use. Drop forging produces high material strength even under dynamic stress. A blank shaped at the correct temperature with correct grain flow, under the correct number of blows, holds an edge longer and resists fatigue more effectively than one where any variable drifted. A well-forged scissor blank, made from quality carbon steel, could last decades. Many modern components stamped cold from sheet steel last a fraction of that. The drop forge was not simply a production technology, it was an organizational declaration. To own a properly equipped forge, with precision dies and trained workers, was to signal industrial seriousness. Manufacturers in this region became early adopters of drop hammers and grinding machines, achieving a uniformity of output previously unseen in the world of cutting tools. Quality became a geographic identity, a regional brand, something worth protecting, and, as history would show, worth counterfeiting. The scissor blank was the foundation of that identity, unremarkable to look at, irreplaceable in function. Long before quality control departments and digital measurement, accuracy was enforced by the die. It did not negotiate. It imposed its geometry onto every billet, provided the temperature was right, the weight was right, and the craftsman was paying attention. Ordinary scissors found in every home. Material intelligence most people never think to question. If uncovering these hidden processes matters to you, consider subscribing and tell us. Which lost manufacturing technique should we document next?